All right, Organic Chemistry 2, Chapter 27, Synthetic Polymers. It's the last chapter in organic chemistry, the last chapter of new material. And we only cover the first 4 sections of the chapter. Notice that it says synthetic polymers. There are natural polymers. For example, a protein would be considered a natural polymer. It's a polymer made up of amino acids. Other natural polymers would be things like starch, so amylose or amylopectin, and glycogen, those are, or cellulose, those are all naturally occurring polymers of monosaccharides that are linked together. But in this chapter, we focus on things that are made in the lab, so man-made polymers. But the same rationale applies where, let's say we're making a peptide or a protein, we're taking individual amino acids and putting them together. Well, what you're going to see in polymers is we're taking individual units and we're putting them together. Now, something I said before I even started recording this video today is that students would be done a disservice if they didn't study a little bit about synthetic polymers after studying organic chemistry for an entire year, because polymers are so ubiquitous in our day-to-day lives. Now, before we get into it, you might want to review some topics, and hopefully you all took the time to read the chapter before coming here today. But we might talk a little bit about sources and uses of alkanes, and I'll fill in any blanks there. Cationic polymerization of styrene, that was brought up in the alkenes chapter. I'm going to go over it with you today. And then radical polymerization, so initiation, propagation, and termination. I'm going to cover all those steps with you today, but these are things that we've seen previously that are going to come up in this chapter. So important things that we need to know before we step in here, but I'm going to cover them with you today. Now, as I was saying, we would be remiss to not talk about polymers before ending a year of organic chemistry. Why? Because they're everywhere. You know, I'm sure that if your eyes are open right now, you're seeing a polymer somewhere in front of you. In fact, it says we make 50 trillion pounds of synthetic polymers every year just in the United States. And you think there's many other countries on the planet. So we are basically dependent on polymers. I mean, if I look just in front of me, I have my cell phone that's made of polymers. I have a flashlight here, a computer screen, my computer, my Apple Pencil, my mechanical pencils are made of polymers. Even the floor here is made of a polymer. You know, basically everything that we see around us, my calculator is made of polymers. The cable that attaches to my iPad is made of polymers. So polymers and plastics, and we use them all the time in our everyday lives. And I'm going to bring up some examples as we go through. But again, we are basically dependent on polymers in our everyday lives. And if you read all of the asides in the textbook, they have come up a bunch of times. I don't demand that my students read those at all, but if you want to go back, you can see that in many chapters before we get to chapters 27, polymers do come up along the way in our textbook. As I told you, a naturally occurring polymer like a peptide or a protein or a polysaccharide, those are made of naturally occurring, monomers that are linked together. However, a synthetic polymer is same thing. It's comprised of repeating units, so it just repeats and repeats, but the monomers are synthetic. These are things that are made in the lab, or they can come from the petroleum industry, and we classify those as synthetic polymers. Again, just to rehash, a biopolymer, that would be something like, we could put here starch. Oh, you could even put DNA in here if you want, DNA or RNA. You could throw that in there. You could put a protein, all of those would count as biopolymers. But again, what we're going to focus on here will be synthetic polymers. Let's take a look at the construction of a synthetic polymer. Many of the polymers that we're going to look at, not all, but many of them are going to be ethylene derivatives. So we just have a carbon-carbon double bond with some kind of R group on it, and we consider that to be a monomer, and then we put them together, and then we end up making a polymer. Now, if you look very carefully at what's happening here, you'll see that what's happening is you're making a bond between this carbon and this carbon right here, but you're removing the double bond, okay? So you do it Again, you make another bond here, you remove this double bond. So the pair of electrons in the pi bonds end up becoming sigma bonds. So we're going to look at the actual mechanism of how a polymer is formed, because there's more than one type of mechanism that we have to know. It says that the shorthand for the polymer is to put the repeating unit in brackets. So you can imagine, instead of drawing a polymer as all these different R groups linked together and add and add and add, I mean, you could add, thousands of them. So what do? We look for the thing that's repeating, and you see these dashed ovals, that in these dashed ovals, I have these repeating units. And so in those that repeating unit, I put it in square brackets like this, and I just put the letter N as a subscript like that, and that tells me that that is my repeating unit in my polymer. We're connecting only the atoms that are in the bracket over and over and over. And if you were to connect those, if you were to repeat that unit over and over, you should get the desired polymer. So we're going to get some practice on that so that we're able to go back and forth between the polymer and the shorthand form. So let's talk about nomenclature. You've covered a lot of nomenclature in organic chemistry. So this is probably a lower order of magnitude of complexity compared to many of the other types of nomenclature that you've looked at in this class. There are systematic names for polymers. Okay, so there are, systematic, just apply this rule and that rule that we use for polymers. It's not even discussed in our textbook. So don't worry about that. The way that we're going to name polymers is by using common names, and those are accepted by UPAC. There's nothing wrong with it. Oops, I was supposed to highlight that. They're accepted by UPAC, so there's IUPAC. There's nothing wrong with it at all. So all we do is, let's say you have propylene as your monomer. Well, if you have the polymer of it, you call it polypropylene, right? If you had styrene and you polymerize it, it becomes polystyrene. So besides names like polypropylene and polystyrene and saran, we give them trade names as well. And I'm sure you've all heard of Teflon, Teflon coated cookware, like frying pans that are non-stick. I'm sure you've all heard of Kevlar because of Kevlar vests, which are, bullet resistant, I would say. Kevlar has many other uses besides that. We use it in Canada to make canoes that are very resistant to rocks and what have you. And saran, as I told you, that's found in saran wrap. So I'm sure that everybody's heard of saran wrap. Anyhow, so that's how we name polymers. And let's say you have a monomer that has two words in it. And I'll show you an example of this in a second. When you have a monomer that has two words like vinyl chloride, you put those two words in brackets. So I'll show you an example in just a few seconds. Let's take a look at some examples and where you would find polymers. And again, I could get anybody in this room, in this virtual classroom, to unmute your mic and say, tell me about a polymer that's around you. You're like, well, the blades on the fan in my room or something are made of polymers, okay? So if we take ethylene, and ethylene is the simplest possible alkene. It's just CH2, CH2. You can call it ethylene or you can call it ethene, but we use ethylene when we're naming the polymer. So the name for the polymer, we give it polyethylene. When we draw the repeating structure of the polymer, what we do, like I said before, is we delete that pi bond. You take and you make a bond off of each side and you put square brackets around it like that. And that's what we have here. That's the repeating structure. Now, where do you find polyethylene? In things like water bottles, like if you buy plastic water bottles at the store. I don't mean like a Lexan bottle, but I mean like just like a cheap bottle of water. At Walmart, if you buy a 30-pack, those are made out of polyethylene, or a trash bag would be made out of polyethylene. Another monomer that I think it's good for students to know is propylene. Of course, if you have this, we call it propene. Propene, that's a perfectly acceptable name. However, the more common name is to call it propylene. Propylene. Okay, so propylene, we make polypropylene, and there's all kinds of uses of polypropylene. Again, to draw the polymer structure, all you do is you remove the pi bond, you take a bond off here, put square brackets and an N, and you get that thing exactly right there. Now it says here that polypropylene is used in car tires. I suppose it's used as a fabric, to enhance the strength of car tires. But it's also used in things like ropes. So ropes that are very resistant to salt water. The next one is polyisobutylene, and hopefully you all know isobutylene by now. So if we have this compound, this is called isobutylene, right? And here's the complete Lewis structure, I guess, or semi-condensed Lewis structure. Same thing, if we remove that pi bond and draw two bonds off of here, we get polyisobutylene, and that's found in things like caulkings and sealants and what else? It even says a basketball. All right, next we have styrene. So styrene is this compound right here, shown at the top. Normally when we draw styrene, we usually just draw, you probably would have seen this when we were doing alkene chemistry, something that looked like that. So this is the same thing. So that's styrene. Just have there, something like that. It's just an ethylene with a phenyl sticking off of it. And you can imagine that from styrene, you can make polystyrene. And of course, you've probably heard of polystyrene being linked to styrofoam. And the original styrofoam was just this. It was a polymer, just polystyrene. However, it was found to degrade under, after a certain amount of time. And so now the new styrofoams that we are accustomed to, those have been doped with, other kinds of compounds that make them more resistant to decomposition and what have you. But again, the same uses apply. You can make a foam cooler out of it, all kinds of different things like that. Next is, so this compound here, this would be called vinyl chloride. So that's two words, right? So when you write out the name of the polymer, you put poly, open bracket, oops, that's not a very good, open bracket, chloride, and then a closed bracket, okay? Anything that's two or more words, we put brackets around it. So polyvinyl chloride, you can imagine that is PVC, and I'm sure you've all heard of PVC pipes. It's used as water pipes, and sewage pipes can be made from PVC. It's got many uses, PVC. The next one is one I'm sure that would catch your eye, or stick to you at least. It's super glue, right? So super glue is made from methyl alpha cyanoacrylate, this compound right here. So it is so activated because it's got a nitrile on it and a methyl ester. And I'll go into more detail about this later on. But basically, you've got two really strong electron withdrawing groups on it, which makes it really reactive with a weak nucleophile, even like water. So that's why if you get super glue on your fingers, even like a tiny bit of water in the moisture on your fingers will cause it to polymerize, and super glue sticks really hard. So we call that poly, open bracket, methyl alpha cyanoacrylate. All right. What else was I going to say? There's also an aside in the textbook. I can't remember if I have it in my slides or not, but some people will use super glue to stick their wounds back together, and I guess there's nothing wrong with using super glue to do that. However, there are variations on super glue where they change the methyl group to an octyl group, and that's called Dermabond. And I'm sure that somebody here has heard of Dermabond before. It's like a liquid bandage because apparently there's something toxic in the polymethyl alpha cyanoacrylate. It's never hindered me from using super glue as a way to stick my, to fix any kind of cut or something that I have. The next one is Teflon, so tetrafluoroethylene. We make polytetrafluoroethylene. So again, same rationale. I'm just going over it one more time. Make a bond off of here. We scribble that out. We put square brackets. We write N, and then you get the repeating unit of polytetrafluoroethylene. And I'm sure you all know that by its trade name, which is Teflon. And I mentioned that before, Teflon. And the reason why Teflon is non-stick, you can imagine that if you have this on top of a frying pan, so let's imagine this is your frying pan here, and that's not a very good frying pan. Here's a frying pan, looks like this maybe, and then you got a handle here. Whoa, okay. So there, you can imagine that if you have this polymer coating it, well, remember that fluorine is a very small element, very non-polarizable because it's so electronegative. Its effective nuclear charge is so high that the electron density around the fluorine is just held so tightly by the atom that the London forces around fluorines is so weak that that's basically why nothing sticks to it. Okay, it's just because of London forces. They're so weak that nothing tends to stick or doesn't stick very well to Teflon. So, which is kind of cool when you think about it. Really neat chemistry in action there. All right, with all that information in mind, let's see if we can tackle a practice problem. It says, draw and name the polymer that results when each of the following monomers undergoes polymerization. So the question that students always ask me is, how would I know what the name of this is? And the answer is, I'll tell you. So I'm going to scribble the name down here for you. This polymer is called vinyl acetate. So if you needed that, I would give it to you. The one on the bottom is called alpha-butylene. Alpha-butylene. I think it's going to come up again in the lecture in a few minutes. But vinyl acetate, if we make the polymer of vinyl acetate, could anybody name it for me? And it's not a, it's just a regular old question. Since it's got two words, right, in the name of the monomer, you'd have to use poly, open bracket, vinyl acetate, close bracket, right? So we're going to make polyvinyl acetate. And how are we going to make that polymer? We're going to convert these carbons from being sp2 hybridized to sp3 hybridized. So look, we're going to put the first carbon, it's got two hydrogens. So 1, 2. Then the next carbon has one hydrogen and an acetyl ester on it. So we're going to put this down here. And then we'll just write OAC up here. There's nothing wrong with that. If you were to just write this and say, this is my repeating unit, and this is called polyvinyl acetate, I would say that's perfect. There's nothing wrong with that at all. In fact, that's probably the answer that's in the textbook. However, if you wanted to make, add some more on there, let's say you added a second molecule like this, I'll add another monomer on it like this. There's nothing wrong with that either. To me, that's still correct, right? Because this is a repeating unit and this is a repeating unit, and it repeats and repeats like that. Polyvinyl acetate. Give me a thumbs up if you follow me on that. Stop me if you don't. Everybody with me on that? Just how to draw the polymer. Okay, it's kind of like connecting the dots, and my students have pretty good abilities at drawing and naming compounds at this point in the class. So for alpha-butylene, alpha is not a word, it's just a prefix. So we'll just call that poly alpha butylene. And let's draw the polymer. So we're going to start with our carbon that has two hydrogens attached to it. So that's a methylene. Then the next carbon has an ethyl group on it. So we'll just put here CH2, CH3. And then we have another hydrogen on it like this. We put that in square brackets. It repeats over and over. And that, my friends, is perfect. Here you go. That's the polymer. That's it. If you got really gung-ho with it and you said, I drew some more, Mr. Dion. If you said, I put another methylene, and then I put another CH, CH2, CH3, like this, there's nothing wrong with that. And you notice that I condensed the structure here instead of making, the bond down here. I just wrote CH, so I partially condensed it. There's nothing wrong with that either. That's totally fine. Both of these are completely reasonable. All right, so now that we've looked at nomenclature and how to go from a monomer to a polymer, let's see if we can do the opposite. This is question 27.2. It's got kind of a long question here. It says sodium polyacrylate, this compound, is a synthetic polymer used in diapers because of its ability to absorb several hundred times its own mass of water. This extraordinary polymer is made from another polymer, polymethylacrylate, via hydrolysis of ester groups. Draw and name the monomer used to make polymethylacrylate. Well, they've given us the structure of polymethylacrylate. It's right here. So if we want to draw the monomer, what we're going to do is we're going to eliminate these two bonds, okay, and we're going to replace them with a pi bond in between those two carbons. So I'm just going to erase that. And what do we have? We have CH2, double bond, a carbon with a hydrogen, and then attached to that, we've got a carbonyl and then O-methyl, just like that. That's all there is to it. And then for a name for that, since this is polymethylacrylate, we're going to get rid of the poly and we're going to get rid of the bracket like that. So that means the name of this is just plain old methyl acrylate. There we go, methyl acrylate. Boom. Everybody with me on that one? Any thumbs ups on that one? I think I could do that, Mr. Dion. If you gave me the polymer, gave me the name, I could identify the monomer. I could pick it out of a police lineup. I could give it a name. Yeah, okay, cool. There we go. Sodium polyacrylate's a pretty neat compound, you know. Something that can absorb that much liquid. Okay, so now we're going to go from section 27.2 into section 27.3. Everything that we've looked at up until now has just been one monomer, and then you make a polymer. But there are many polymers that are made from more than one type of polymer. Thus, what we're going to do is discuss the different ways that they can be joined together and some of their properties, and we're going to look at some examples of what are called copolymers. Again, everything that we've looked at up until now has been a homopolymer, so just one thing. So examples would be things like Teflon that we looked at, you know, polystyrene. What else did we look at? I don't know, polyisobutylene. We could put here super glue, etc. Okay, everything that we looked at up until now. But now we're going to talk about copolymers, and I actually brought up the word saran earlier on. The reason why is because I know everybody's heard of saran wrap. So a copolymer is made from two different monomers, but you can alternate them or you can group them together. So let's take a look. It says here that saran, again, is a copolymer. It's made from vinyl chloride, which we've seen already today, and vinylidene chloride. You notice that the only difference between these two compounds is this one has an extra chlorine on it. So vinyl chloride and vinylidene chloride. So instead of trying to call this some wacky name like vinylidene, you know, there's nothing like that. It's a lot simpler to just give it a common name, isn't it? And saran wrap is obviously a brand name, but that's what it's made out of. It's just a polymer of vinyl chloride and vinylidene chloride, and of course it's transparent and it's got an elasticity to it, and it's able to hold on to some types of surfaces. So the whole idea is that saran, the reason it was developed is because when you have a copolymer, it's going to have different properties than its homopolymers, right? Saran is very different than PVC and very different than polyvinylidene chloride, right? And that comes as no surprise to any of you. You've studied enough organic chemistry by now to know that when you change the structure of a compound, yeah, it's definitely going to have different properties, won't it? You can imagine that scientists are still today, I don't know how hot the area is in terms of research, but people are still working on new polymers all the time, you know, developing new polymers. So what they do is find ways to mix monomers and make novel polymers that can, you know, enhance our lives. So we went over saran and how that's used in food packaging. So we'll keep moving along from there. But the next one is SAN. So all those dishwasher safe plastics and things like in Tupperware and stuff, those are usually made from styrene and acrylonitrile together. So styrene and acrylonitrile, right? SAN. Anyhow, so that's another example of a copolymer. Another one is ABS, and I'm sure that you've all heard of ABS before, you know, an ABS bumper or a helmet. It's like you know, plastic rubbery, you know, or plastic material that's got some give to it, some flexibility. And the ABS stands for acrylonitrile 1,3-butadiene and styrene. Of course, they didn't put them in the right order here, but you get the idea. So they mix these different monomers together to make ABS, and of course, we get new materials with new properties. So again, you can see how just by modifying a polymer, you can make really neat things. And you know, we're always trying to push the envelope and develop new polymers. Let's take a look at two more. The next one is butyl rubber. This one is something I'm sure you haven't heard of a whole lot, but butyl rubber is just, if you've ever seen a rubber tree and you've ever heard of the history of rubber and how vulcanization was developed, which is not the topic of today's lecture, but you know that when rubber was first isolated, it had very limited uses and the first tires wore out really quickly. So, you know, scientists are always looking for ways to increase the strength and the longevity of rubber. So they mix isobutylene and isoprene, and they make this butyl rubber, which is found in things like inner tubes. And the last one is Viton. I don't know if anybody here has ever heard of Viton. I had never heard of it until I got into graduate school. It's made from hexafluoropropylene and vinylidene fluoride, so two fluorinated polymers. And I told you that fluorinated polymers are really not sticky, and they're also very tough, right? You think about Teflon, that, yeah, sure, once you've made 1,000 grilled cheese sandwiches, yes, the frying pan does tend to break down. However, the fluorinated polymers are very strong. And Viton is a really neat polymer. The reason I used it as a graduate student and in big pharma was when we were doing reactions at high temperature with strong acids, and you needed to seal your reaction vessel, we would oftentimes use Viton gaskets, because if you just used a conventional rubber gasket, it would just get destroyed by a strong acid, whereas Viton is very, very strong. So it's something that I learned along the way in life. And, I don't use Viton a whole lot now, but a very strong polymer. Moving right along with this whole copolymer thing. Now, something that I didn't really address is that, I told you, for example, that Saran is made out of two different, monomers. And I said, okay, well, butyl rubber is made out of two polymers. But the way that it's kind of laid out in the book, it makes you feel like, well, everything must be a 50-50 mixture. I must have 50% this monomer, 50% that monomer. But if you go back here, just for example, butyl rubber, butyl rubber is actually 98% isobutylene, and it's only about 2% isoprene. So just because they're in here doesn't mean they're mixed exactly 50-50. And I don't know the percentages of all of them, but I do know that when you make a copolymer, there's different ways that you can put the monomers together, and you need to know these definitions. So let's go over them. They're pretty, I don't like to use the word self-explanatory, maybe slightly intuitive. Maybe I could kind of say it that way. The first one is a random copolymer. So you can imagine if it's random, there's no rhyme or reason to it. You just have some of one monomer followed by another, and another, and maybe so, so there's no way to predict the way the monomers are going to be linked together. It's just random. Now, the next one is also, I think, a little bit intuitive, an alternating copolymer. So that's where you have one and the next. So A, B, A, B, A, B, A, B, like that. And something that our textbook tells you is that even if you have an alternating copolymer, it's very rare that it would always perfectly alternate A, B, A, B, A, B, A, B. There's going to be like, a BB and an AA in there somewhere, because it's very difficult to control these things to make them grow exactly, AB alternating like that. But generally speaking, they'll be alternating. So we've got random and alternating in a line. The next one is a block copolymer. And you can imagine that it means a block of monomer units, and then another block, and then another block. So you kind of get like little chunks linked together. And then this is what I think is one of the most interesting ones, is a graft copolymer. So they make a whole homopolymer on top, and then they graft homopolymers that are different onto that. So again, the take-home message here is that if I was to ask you a question on your quiz, you would need to know the difference between random, alternating, a block copolymer, and a graft copolymer. Generally speaking, students don't tend to struggle with these a whole lot once you get a little bit of practice in it. It tends to stick in your brain. But with all that information in mind, let's take a look at a practice problem. Here it just says, draw the region of an alternating copolymer that's made from styrene and ethylene. So let's just draw a styrene molecule, which is this. So it's an ethylene with an aromatic ring on it. It's not very pretty, is it? Fix that up. So we have a styrene. That's not even any better. Anyhow, and an ethylene. I try to color code this, but then I always feel weird about the way I draw the bonds between them. But anyhow, let's take a look. So we've got styrene and ethylene. So what that means is it's going to go styrene, right? And then ethylene, and then styrene. And then I'm just trying to show you an example here of alternating. So then styrene, and then ethylene. And I'm sure you all figured that out, that it's going to alternate. So what are we going to do here? Remember, this represents CH2, and this represents CH. This represents two methylenes, two CH2s. And thus, the way we're going to put it together is like this. We're going to have a methylene, then this methine, then the aromatic ring. Then we're going to link that or bind that together with a unit of ethylene. So we're going to have CH2, CH2, like that. Now, if you were to stop here and just put brackets around that and put N and say that's the repeating unit, that I would give you 100%. That's totally correct. There's nothing wrong with that at all. In fact, that's right. And that's probably the answer that they have in the solutions manual. However, if you're the kind of person who likes to doodle and draw an extra, couple of the monomers in there. So if you did another monomer from the styrene and another monomer from the ethylene, there's nothing wrong with that. I don't see why not. Like that. But either way, you just have to understand that it goes, styrene, ethylene, so on and so forth. And there we go. Everybody with me on that? Thumbs up on that one. Everybody thinks they can do that? Or any questions about that one? So alternating, remember, alternating is just AB, AB, AB. Okay, cool. Well, let's take a look at the next one. So this one just says draw a region of a block copolymer constructed from propylene. So propylene is this. Okay, it's just propene. And vinyl chloride. So vinyl chloride is this. So it's a double bond with a chlorine on it, like that. And when it says, hey, draw a block copolymer, I'm not picky about how many you put together for a block. You can put 2, you can put 3, you can put 4, you can put 5, you can put 10 if that's really what you want to do. I don't see the need to do that. What I think we're going to do, or what I want to do, is why don't we put 3 propylenes together, and then we'll put 3 vinyl chlorides together, and then we'll call that a day. Okay, so we'll keep it, kind of simple. So let's start with our propylenes. We'll do 3 of those. We have CH2, CH with a methyl coming off of it, like this. We have another one, so that's 1, 2. Then we'll add another one, 3, like that. Okay, so we've got all that done. Put our open bracket there. Now we're going to add all the vinyl chlorides. I'll put a black bond there so everybody can distinguish. So then we have 1, 2, and 1 more. And that's it, my friends. That's it. Nothing more to it than that. Now, if you want to draw it using a bond line structure instead of a condensed structure like this, there's nothing wrong with that either. I would say the kudos. That's great. So you could just make it like this. So there's 1. So look, here's where I have my open bracket. So then I've got CH2CH, CH2CH with a methyl, CH2CH with a methyl. Then I have the bond to my CH2 with a CH and a chlorine. Oops. CH2, CH with a chlorine. CH2, CH, oops, getting carried away here, with a chlorine like that. And then you put brackets around it like that. Either one, they both represent the exact same thing. If you want to draw the condensed structure when you're practicing, do it. If you want to draw a bond line structure, well, you can imagine that our book, when we get into section 27.4, he's usually going to draw them like this, okay? But if you find it easier to draw them like that, no problem. No problem. As long if it's right, it's right, As long as my students get the right answer, that's the main thing. Let's try one more. Let's try one more before we get into section 27.4. It says identify the monomers that you'd use to make this alternating copolymer. So we've got 2 monomers in it. Got this one here, and then we have this one right here. So let's see if we can connect the dots here. The one on the left, you've got CH2, and then you're going to have a double bond, and then it's going to have a methyl and a methyl like that. So hopefully you recognize that from earlier on. That is the same thing as this compound. Does anybody know the name of that compound? The common name for it? It's got a systematic name as well, but there's a common name for this compound. It's called isobutylene. So that's ice. It's a gas at room temperature. Isobutylene. So isobutylene is one, and the one on the right is CH2, double bond, CH, and then an aromatic ring. So that's the same thing as this, where you have an aromatic ring. Then you have this coming off of it. So that is styrene. Styrene. That's not very pretty. Styrene. There we go. And that's it. So that's how we identify those monomers. Now, students are going to ask me, do I have to know vinyl chloride, vinylidene chloride, all of these monomers? I would say that any monomer that we look at, you should have an idea. So you should know things like isobutylene, styrene. You should know propylene. You should know vinyl chloride because PVC is so common. Obviously, and I don't mean that in a flippant manner, but you should know ethylene. It comes up all the time in organic chemistry. Other ones that I would expect you to know from here, out of here, well, it's kind of the same old thing over and over. But vinyl chloride, I think, is important. Vinylidene chloride, I'd put that in there as important too. And what else? Oh, the one that's used to make super glue. Like, so I think you should know. I think you should know tetrafluoroethylene. So that's pretty standard. And yeah, I think that's about it. Those are the ones I would expect you to know. I think it'd be a good idea if you knew what super glue was. Not a bad idea because people love to ask questions about super glue just because it's such a common organic polymer. Maybe one of the most common. Everybody knows what super glue is, right? All right. So those are the ones I would expect you to know. And I bet you that you know a bunch of them already. I've seen them so many times in organic chemistry that there you go. The last section that we cover in this chapter is section 27.4, where we're going to start classifying polymers by the reaction type that we use to put them together. So the type of reaction is covered in section 27.4. The mode of assembly, that's covered in 27.5. The structure is covered in 27.6, and the properties is covered in 27.7. We are going to skip all of these three sections. So we're going to skip those. Thus, the last section that you're going to do with me in this class is the type of reaction that's used to put a polymer together. So there's basically three types that we're going to look at, which is radical addition, cationic addition, and anionic addition. But the rest of it, where it says skip, if you want to read that as an FYI thing for your own information, go ahead. There are no questions on the final exam about it. There won't be any questions on your quiz about it. And I've never seen a question on an MCAT about any of those sections. If you go into the MCAT or DAT materials, usually what they would ask you would be something like they would give you the structures. And I'm just saying, like, I can't predict every single MCAT question in the universe, but the kind of thing that they would do is they would give you two monomers and then they'd say, okay, which one of these is the alternating copolymer or something like that? Which one of these is the block polymer? Or which one of these is the correct polymer of this compound? Something like that, just to make sure that you're able to kind of put a polymer together. All right, so what we're going to do is we're going to take a short break, and then we're going to come back, and we're going to talk about the types of reactions that can be used to put polymers together. We're going to start out with free radical addition, and then we'll look at the two ionic mechanisms that can be used to put polymers together.